Welcome to this video on logarithms, doubling time and flattening the curve. Some people who watched my original video on exponential growth asked if I could say a little bit more about logarithms, so here we go. Now most people know that if you put an extra zero on the end of a number, it goes up by 10, 100, 1,000, 10,000 and so on. And some people will also know they could be written as 10 to the 2, 10 to the 3, 10 to the 4, etc. Now those numbers 2, 3, 4, 5, 6 are the logarithms. They can be used to represent the whole number. So 6 is the log of 1,000,000. 2 is the log of 100. 100 could be written as the number who has the log of 2. But all numbers could be written in this way, even those that don't make an exact multiple of 10. For example, 3.16 has a log of 0.5. 10 to the 0.5 is 3.16. The log of 316 is 2.5. The log of 200 is 2.3. Now how do we know those things? Well, we have to look them up. In the old days we used an old logarithmic table, log tables. Now you can just press the right button on your calculator. Now in the old days we used to use those log tables to help us to multiply numbers. Long multiplication is hard, but addition is quite easy. And it turns out that if you want to multiply two numbers together, all you have to do is to add their logs, work out what the answer is, and then work backwards. So for example, in this case, the answer is 10 to the 3.95, and as you can work out what the log is, 3.95 is the log of 8,912, and so the answer to that long multiplication sum is 8,912.3. Of course, you can also try that on other examples too. And if you look here, there's a couple of others that you might want to follow through if you pause the video. Now in my video on exponential growth, I refer to the number e, as in y equals e to the kx, and also to natural logarithms. Now all natural logarithms are the same as the logs we just talked about, but this time instead of using the base 10, we use the base e, a particular number which has got the value of roughly 2.72. So for example, the number 54.7 is 2.72 to the power of 4, so that the log, natural log of 54.7 is 4, and so on. And we can use these in exactly the same way as we use natural logs. And if you can see here, there are various examples, so that the natural logarithm of 10 is 2.3. The natural logarithm of 100 is 4.61. The natural logarithm of 1,000, 6.91. And those numbers can be useful when you're looking at a graph where data has been plotted according to their natural logs. Again, if you want to stop the video, have a look. You can do exactly the same kinds of multiplications as you could with logarithms to the base of 10. Now all of that information on logarithms you can put to one side if you like, but this section here is probably what you would like to know about if you're interested in finding out how natural logarithms are used to help plot the kind of exponential growth that we are seeing in the development of the coronavirus outbreak. Now here I've got data in a table for the last couple of weeks or so for the total COVID-19 deaths in the UK. And then in the final column, I've worked out their natural logs, LND, and then what I'm going to do is to plot those on the graph. And we'll show you two graphs together. On the left-hand side, we'll show just the plot of the deaths in the UK with the actual numbers. On the right-hand side, then I'm going to use a logarithmic graph plotting the natural logs of D rather than the actual totals. So let's go, and you can see the points developing over time. Now you can see how suddenly the exponential curve on the left begins to pick up, while the right-hand curve, the logarithmic graph, stays broadly speaking a straight line. And I've drawn in the general trends there that you can see. While the left is clearly an exponential curve, or at least it's clearly an exponential curve, because the right-hand graph, the LND graph, shows that it's a straight line. And if the logarithmic graph is a straight line, then the curve on the left is indeed an exponential curve. Now, as I also explained in my other video, the importance of the natural log graph is that you can also work out something called the growth constant K by working out the gradient of that line. And in this case, I've calculated that the growth constant of the increase in death totals in the UK is approximately 0.21. Now, what does that number mean? It means that the totals are doubling roughly every 3 days, as you can see in the data on the left. And that is going to continue in that way unless we can lower that value of K. And in other words, we can start to flatten the curve so that the numbers aren't increasing quite as rapidly as they are at the moment, doubling every 3 to 4 days. Now again, there's some maths here that not everybody will want to know, but the chart on the right gives you some idea about how the size of a growth constant compares to the doubling time, if you like, how long it takes a total to double from where it was before. If, as in the UK at the moment, you've got an exponential growth constant K of around 0.2, 0.23, then the doubling time is about every 3 days, and so the death totals appear to be doubling over that period of time. What we need to do in the UK is to lower that constant further, perhaps down to 0.1, so then the doubling time will increase to about every week. Of course, that'll still mean the death totals are going up, so we need to drive the growth constant down further, so that we start to reach a stage where death totals are hardly increasing at all. Now I want to finish by looking at the actual latest data from 3 countries, the UK, Italy and Spain. And it's actually quite useful to look at the logarithmic graphs for Italy and Spain, because you can see that actually a line that perhaps a week ago was quite steep in its curve, now towards the right-hand side of that graph, that line has started to flatten off. So in fact, the growth constant in Italy, the gradient now is only about 0.09. So the totals, although high as we all know in Italy, are now taking more than a week to double. The growth is slowing down. The same in Spain, which is perhaps a little bit behind Italy, higher totals than in the UK, but again, the growth constant has fallen. Totals are now taking about every 4 or 5 days to double. Now in the UK, worryingly, at the minute, our growth constant has stayed fairly steady over the last fortnight, at around 0.21. So our totals are still growing quicker than in Italy and Spain. They're taking every 3 to 4 days to double, as I explained earlier. So we've really got to make sure that we are, hopefully, taking steps that mean that we will also follow the trend in Italy and Spain so that their growth constants start to fall and their curves start to flatten. And I want to finish by stressing that point, because some of us who are drawing exponential curves and explaining exponential growth have been accused of suggesting that that growth will carry on, and therefore the death rates will just keep getting higher. That's absolutely not the point that I'm making, and I made that clear in the first video. If we keep flattening the curve, if we keep lowering the growth constant, if we keep increasing the doubling time, then actually that curve will not continue to grow exponentially, but will have an S-shaped curve that will eventually flatten off and can get to the stage, as some other countries have done, where the death totals are beginning to stop and the increase has ceased altogether in some cases. I hope that update has been useful for you, and hopefully it shows you that we can continue to flatten the curve, but only if we keep up the pressure to make sure that everyone has the protective equipment that is needed, that our hospitals have the right ventilators and testing is carried out on a far greater basis than at the moment, that workers are paid in full rather than having to go into work because they're concerned about their income. These and the other vital steps that are required to flatten the curve are the ones that we've got to continue to fight for.